Hello and welcome to Podcast.init, the podcast about Python and the people who make it great. When you're ready to launch your next app or want to try a project you hear about on the show, you'll need somewhere to deploy it, so take a look at our friends over at Linode. With 200 gigabit private networking, node balancers, a 40 gigabit public network, fast object storage, and a brand new managed Kubernetes platform, all controlled by a convenient API, you've got everything you need to scale up. And for your tasks that need fast computation, such as training machine learning models or running your CI and CD pipelines, they've got dedicated CPU and GPU instances. Go to pythonpodcast.com/Linode, that's Linode today to get a $20 credit and launch a new server in under a minute. And don't forget to thank them for their continued support of this show. Your host as usual is Tobias Macy, and today I'm interviewing Ariya Shajii about Seek, a programming language built for bioinformatics and inspired by Python. So Ariya, can you start by introducing yourself?
Sure. I'm a fourth-year PhD student at MIT CSAIL, working with Professors Bonnie Berger and Saman Amarsinke. Before Seek, I worked on various other genomics applications like genotyping and sequence alignment for a particular kind of third-generation sequencing data. And now for the past couple of years, we've been working on this project. So that's sort of a little bit about me.
And do you remember how you first got introduced to Python?
So the first language I learned was actually Java in high school. And shortly after that, I stumbled across Python, and I think I kind of gravitated towards it because it seemed like a language that was really targeted at people who don't have a computer science background, and sort of from its design and everything, it's very simple, clean syntax, and the large community kind of led me towards Python. So that's how I first encountered it.
And so now you're working on this Seek project. I'm wondering if you can give a bit of a description about what it is and your motivation for creating it and how you first got interested in the area of bioinformatics.
Sure. So I guess I'll just say a few words about what Seek actually is. So sort of at a high level, Seek is essentially a domain-specific language for computational genomics and bioinformatics. Language-wise, it's based largely on Python. So you can think of it as sort of a Python implementation, on top of which we've added a few domain-specific features, types, and compiler optimizations. The key difference between Seek and CPython, for example, is that Seek compiles to LLVM IR with no runtime overhead. So the language itself is completely statically typed, and unlike CPython, we have no runtime type information or anything like that. And so as far as the motivation is concerned, really what motivated Seek was the fact that we were looking at these different genomics applications, and what we realized was that they're doing different things at a high level, but they're essentially reusing the same primitives. So they're operating on sequences, DNA sequences, for example. Those are strings of ACGT. They're dealing with really big data. They're doing operations like sequence alignment, sequence indexing, hashing, stuff like that. So they're all sort of using these same set of building blocks. And that's what really motivated us to build a language that exposed these operations as primitives, and the compiler that understood them and could do optimizations on them. We tried for a really long time to build a high-level language that exposed these primitives as sort of coarse-grained building blocks that you could glue together in different ways. And ultimately, we actually spent like a year and a half trying to do that, and we essentially found that it was impossible. Like in bioinformatics, there's just too much, yes, they're using these primitives, but there's so much stuff interspersed in between that to build a high-level language that had just these building blocks was essentially impossible. And I think a good analogy for that is MATLAB, right? So MATLAB is like a language for linear algebra, but it's actually a low-level language, right? Because you can't express all the things that are relevant to a linear algebra application with just matrix operations alone. You need some low-level infrastructure, and I think bioinformatics is really similar. So that's why we kind of settled on Python, mainly again because of its appeal to non-programmers and the large community that it has. But we still need the performance. Biological data is growing really fast. It's like much faster than Moore's law, and because of that, performance is really critical in our domain. So that's why we sort of took Python and re-implemented it from the ground up in a statically typed way with no runtime overhead. So that's sort of the motivation for Seek. In terms of bioinformatics itself, I think the reason that I sort of gravitated towards it was just because it was I don't know. I wish I had like a more concrete answer, but it's a really cool field, I think, and it's a really concrete application of computer science. So I think that's sort of why I really like this field.
Yeah, it's definitely an interesting area, and it's exciting to see some of the ways that computational power can be applied to the realms of biology to get some more concrete and in-depth understanding than what we've been able to do previously.
Mm-hmm. Definitely.
And do you have much experience in the past of implementing different languages and compilers, or is this one of your first forays into that space?
So, so my research has always been basically bioinformatics, but on the side of kind of had a few toy projects here and there that were compilers. So I have a little bit of knowledge, nothing really like super formal, but just from personal projects that I've worked on in the past. But I'd say this is definitely the biggest compilers related project that I've been a part of.
And you mentioned that in some of the other available languages and runtimes that there weren't the necessary primitives specific enough to bioinformatics to be able to get the performance that you were looking for. And so you went down the road of creating this custom implementation, and you also targeted Python as the syntax for it. And I'm curious, for somebody who's already working in Python and maybe using something like the BioPython packages for doing some sort of bioinformatics processing, what might motivate them to consider migrating their work to Seek, even if they already have an existing code base? And what are some of the potential challenges that they might face in that conversion?
Sure. So one of our goals is basically to make the Python to Seek transition as seamless as possible. So we're not quite at the stage where you can literally take an entire pre-existing Python code base and run it in Seek. You'll probably need to change a few minor things here and there, but that we're continuing to close the language gap, and we're hoping to at some point in the near future get to that stage. But if you have some small snippet of Python code, most of the time it should just work as is in Seek. About BioPython in particular. And maybe some other libraries just the same. I think one of the main reasons for switching would definitely be performance, right? So BioPython is a pure Python library, and we've actually done a few benchmarks against it, and Seek is substantially faster, especially if you're dealing with these huge data sets. Now, one thing I will mention actually is interesting is we're actually implementing BioPython in Seek. So BioPython has a pre-existing API. We have a lot of the same functionality, and we're in the process right now of actually implementing BioPython's API using the primitives that are available in Seek. So again, I think the point is to try to make that transition as seamless as possible. But for someone who's really interested in performance, I think Seek would definitely be a pretty good alternative to BioPython. I think another important point when talking about the difference between a language like Python and a language like Seek is sort of the metadata overhead, for lack of a better term. So if you think about a linear algebra application that sort of does operations on a few really big matrices, most of the time there is actually just spent in the linear algebra kernels that are, hand optimized C or Fortran kernels. And you really only have a few objects that exist in your Python application. In bioinformatics, or a lot of these genomics applications that we're interested in, the situation is really different, where you have potentially billions of sequences that you're processing at any given time. So any metadata overhead or runtime type information or per object overhead adds up really quickly. So I think that was also one of the motivations to build Seek, that sort of eliminated all of that overhead. So I think that's another reason why Seek might be a good choice for those kinds of applications.
And in terms of the actual code bases that people who work in bioinformatics are going to be writing and collaborating on, what is the general scope and scale of those types of projects in terms of the sort of complexity of the applications and the maybe number of different code files? Is it something where somebody writes a fairly straightforward script to brute force through these different sequences? Or is it something where people are going to be leaning heavily on libraries and wanting to integrate with something like web frameworks or other components of the ecosystem?
Yeah, that's a good question. I think it varies a lot. There are definitely applications where, I mean, there are cases where you're doing some kind of ad hoc analysis and you really only have a single script that you're worried about. There are definitely a lot of cases where you have some bigger project that you're not necessarily relying on external libraries, but just the project itself is bigger and you have, multiple source files or something like that. And then, like you said, there are definitely cases where you're relying on external libraries, probably not web related, but definitely, things like machine learning frameworks, for instance. So I think it varies a lot. And I think because of that, it's really important in Seek to have interoperability with other frameworks to be a priority, and that sort of has been a priority for us. So I think it definitely varies a lot based on your concrete application.
For the primitives that you're incorporating into Seek, you mentioned that there are some elements that are lacking in different implementations, and I'm curious what your process was for identifying what the useful primitives were and some of the algorithms to bake into the implementation of Seek to simplify the work of people working in bioinformatics.
Sure. So I think that's actually been one of the hardest things to do because, again, we spent a really long time trying to design a language that sort of isolated these primitives and just exposed them in a higher level language. And the reason for that is because, abstractly, you have these primitives like sequence alignment, for example, which would be like a Smith-Waterman dynamic programming algorithm, or some kind of sequence indexing, whether you use a hash table or FM index is also a very common data structure used in genomics applications. But when you actually look at implementations of these things, they vary so much from case to case that it's really hard to provide these things as sort of fixed coarse-grained building blocks. So again, this was why we settled on a much lower level language. But having said that, there are definitely things that are essentially ubiquitous. So sequence types, again, that's if you're dealing with DNA, that's strings of A, C, G, T, or you can also have an N base there, which is like an ambiguous nucleotide. Sequence types, Kamer types, which are also frequently used, those are fixed. So sequences are arbitrary length. Kamer types are fixed length K sequences, and you can do things like 2-bit encode those and stuff like that. There are very common operations like reverse complement, for example, where you take a sequence and you physically reverse it, and then you swap A's and T's and C's and G's. That's a very common operation that's done on sequences and basically any genomics application. Again, these string matching algorithms like Smith-Waterman or Hamming distance calculations. So these are sort of the things that we thought were useful to implement in Seek. But I think the other benefit of Seek is that it's a compiler, so we can actually do higher level optimizations that a library couldn't necessarily do. So for example, if you take reverse complement has various algebraic rules. So if you take a sequence and you reverse complement it twice, then you get the same sequence back. So a compiler that actually knows about these things can exploit those algebraic rules and do optimizations that a library couldn't do.
And then for the target audience of Seek, is it largely people who are working in the sciences who just need to be able to process the data that they're coming from? Or is it also common that there might be a set of programmers on staff who work with the domain experts to be able to understand the scope of what they're trying to work with and then they implement the actual applications for them? And curious what types of challenges that poses in terms of how to approach some of the interface and workflow for the people who are actually using Seek in their day-to-day work.
Sure. So I think Seek as a language, I think, is in a sort of a unique place because it, in a way, bridges the gap between a really usable language like Python and a performant language like C or C++. And because of that, I think if you're someone who is not necessarily an expert in programming, but is, let's say, a biologist or something like that, and you're trying to analyze some really large data set, I think Seek that's someone who we actually designed a language for. It's supposed to be something that someone who doesn't have a background in programming or software engineering can pick up relatively easily and use. But at the same time, someone who is, let's say, like an algorithmist and they're designing these really performance critical applications for, sequence alignment or sequence assembly or what have you, that's also someone who I think could benefit from Seek because, we do a bunch of these domain specific optimizations that are pretty difficult to replicate by hand. So I think both sides of the spectrum are sort of people who we're interested in targeting. And again, that's sort of a tall order, but definitely something that we've thought a lot about.
For the overall workflow itself, what are some of the tooling elements that you have implemented to simplify the overall workflow, and how might the actual development process differ for somebody who's used to working in Python? I know that at least for the time being, you don't have a REPL, so that is one impact, but what are some of the other elements that might differ in terms of how people will approach building things with Seek versus what they were doing in Python?
Sure. I think that's probably the area that we need to work on the most. So, we have, for example, Seek has a debug mode that gives you nice stack traces and all sorts of things like that, just like Python does. But again, Seek compiles to LLVM. So it's definitely the debugging process for Seek is more challenging than it is in Python. So I think that's definitely something that we're hoping to work on in the near future to sort of give people the tooling and the debugging support that if they come from a Python background, they're familiar with. I think the other interesting thing in that regard for Seek is that because it's a domain-specific language, we could actually do things like domain-specific debugging, for instance. So, if you're processing sequences and you're aligning sequences, we could potentially implement something like a domain-specific debugger that lets you, visualize alignments, visualize sequences, and all that kind of stuff. So I think we're not quite where we want to be in terms of debugging and tooling and all that kind of stuff. And the primary reason for that is really just manpower. We haven't had anybody, we're just sort of limited on manpower. So, but again, that's something that we would definitely want to work on.
And because of the fact that the syntax is very similar to Python, are you able to lean on any of the existing tools such as linters or static analysis that's available to the Python ecosystem and modify that to work with Seek as a sort of shortcut to be able to get some of those tooling elements in? And then another aspect of the workflow and tooling is the question of being able to test the applications that you're developing with Seek. And I'm wondering what facilities you either currently have or are planning on.
Sure. So in terms of existing Python tools, that's not something we've actually explicitly explored, but I think it's something that definitely makes a lot of sense. Again, like the syntax is almost identical to Python. We've added a few extra language features like pipelines and pattern matching. So I think we might have to make some modifications to some of those existing tools that you mentioned, but that's something that definitely is in the realm of possibility. So for testing, we actually have a testing framework in Seek that is kind of similar to what it is in Python, but essentially what you can do is you can annotate a function with the test decorator, and then you can have asserts in that function that they won't terminate the program. They'll actually just like fail the test if the assert fails. But I think it would be really nice to sort of expand that and maybe even implement some of the testing facilities that exist in regular Python into Seek. And again, the fact that we haven't done that is really just because of manpower. We just haven't had anyone to work on that yet. So
for the actual implementation of Seek itself, I know that the syntax is, as you said, largely similar to Python, and I'm wondering how you approached the actual construction of the language and the compiler, and if you were able to leverage any of the elements of the CPython implementation, or at least use it as a reference for things like the tokenizer or anything like that for being able to build the parser and the compilation and some of the underlying architectural decisions that you've made as you have gone through implementing Seek.
Sure. So a lot of the language design, thankfully, was essentially just dictated by Python. So, Python behavior and semantics and, of course, syntax is basically all present in Seek. On top of that, like I said, we've added a few features like pipelines, for instance, which are a pretty natural abstraction for thinking about processing genomic data, pattern matching, which you might find in other functional languages. A novel aspect of that in Seek is that we actually allow genomic pattern matching. So you can match sequences and you can have, wildcard bases or like stars, like a regular expression, stuff like that. And some of the new types that I talked about. We don't reuse any components of CPython. I think the parser is something that potentially, that's actually something that we could possibly reuse. Again, we have to add support for some of these other language features, but Python's parser is something that we could potentially build on. In terms of the runtime, our philosophy when designing the runtime was essentially just to make it as minimal as possible. So all of the core types like lists, dictionaries, and sets, and even a lot of the functionality of types like integers and float and string and stuff like that, more primitive types, are all implemented in Seek. So we have a small runtime library mainly for garbage collection and a few hand-optimized, SIMD-optimized functions for sequence alignment. But our goal has basically been to reduce that as much as possible and implement everything that we can in Seek itself. So that's sort of been our design methodology so far.
Because of the fact that you are using the Python syntax as a reference, I'm curious how evolutions to the language are going to be reflected in Seek itself and what plans you have for being able to maintain future compatibility as the language evolves and any potential challenges that you anticipate as a result of that.
Yeah, I think that that is definitely a challenging problem. Like, as you make changes to Python, then we'll sort of have to play catch up a little bit, at least for the short term. Yeah, I think, again, your suggestion of using Python's parser, for example, might actually help in that regard, because it'll sort of make it easier possibly to integrate some of these language changes. But I think Seek being a separate language that's essentially independent from CPython, I think that's definitely a challenge to think about. Yeah.
And you mentioned that when you first started approaching this problem, you spent a year going in a different direction before you ended up with the current direction of building Seek. And from the time that you actually started building this custom runtime, I'm curious how the overall scope or direction of the project has evolved and how much that differs from your original conceptions of it.
Sure. So I think Seek today, really, it can be used as a general purpose language. Is probably best suited for scientific applications that don't rely on Python's dynamic features, some of which we've had to get rid of. But if you have some scientific application that isn't dynamic in nature, I think Seek could be a good fit, even if it's outside of bioinformatics. And again, being a low-level language, we've talked a lot about extending to other fields of subfields of bioinformatics. So right now we focus mostly on computational genomics, but there's more to bioinformatics than that. There's phylogenetics, for example, or population genomics. And I think Seek is in a place now where we can potentially target those fields as well. And again, when we started, like I said, we started by thinking about a much higher level language. And I think if we had gone that route, it would have been much more difficult for us to expand to some of these other areas. And like I said, even in other domains outside of bioinformatics, I think Seek can potentially be applicable. So at this point, again, our domain of interest is still bioinformatics, but I think Seek can definitely be a useful tool even outside of that field.
And so as far as the actual bioinformatics field, I know that when looking through the documentation for this project, it alludes to the fact that there is a lot of sort of messy code or inconsistent approaches to problem solving in terms of the way that the software is developed and challenges in terms of the speed of execution. And I'm wondering what impact you anticipate Seek having on the overall domain of bioinformatics and genomics and some of the standards that could be implemented in terms of the training of people who are working in those fields to improve the overall capacity for being able to run these analysis and the impact that this increased speed has on their ability to perform meaningful research.
Sure. So we hope to see a lot more tools and methods being written in Seek in the coming months and years. And I think the benefit that would have is not only would it sort of give everyone a unified framework for bioinformatics software development, but optimizations and features that we add in future versions of the C compiler could even be applied retroactively to existing software, right? So if someone writes a piece of software today in Seek, and however many months down the line we add support for a GPU backend or FPGA backend, then our hope is that that software that was written today could just run as is on those backends, or same for any other compiler optimizations that we add. And I think really, like, in an ideal world, Seek would allow bioinformatics software to sort of keep pace with the growing data that, again, is sort of really outpacing, Moore's law. And I think by 2025, it's predicted that genomic data will even have surpassed Twitter and YouTube data. So it's a really, really fast growing data set. And I think Seek sort of gives us at least one tool to keep pace with it.
And in terms of the data sets, do you find that there are a large volume of information that's available in the public domain for people to be able to do their own experimentation and test out Seek with those data sets? Or is it something where a lot of the information is held in proprietary data sets by different companies working in the biotech industries or the pharmaceutical industries? And any challenge that you've seen in terms of being able to make Seek available and get it in the hands of people who are doing this types of research, or any collaborations that you are either currently engaged with or seeking to be able to get that feedback to help evolve the language?
Sure. So I think in terms of data, it's sort of a combination of both. There's definitely a lot of publicly available data out there. So for example, there are many databases. One of them is SRA, Sequence Read Archive, and that has a ton of publicly available sequencing data. So I think there's a lot of data out there. In terms of collaborations, Google Cloud Life Science has actually recently reached out to us to talk about running Seek on the cloud. So that's something that we're actually starting to work with them to develop a cloud backend for Seek. And I think that's something that we're really excited about, especially again, as the scale of the data increases, to have something like a distributed computing backend for Seek, and in general, a compiler that can perform not only single machine optimizations, but optimizations that are relevant to a distributed computing environment. I think that's a really powerful tool. So
as you have been building the Seek language and working on improvements and experimentation with it and working with some of the end users, what have you found to be some of the most interesting or unexpected or challenging aspects of building a language for this problem domain, and just some of the overall elements of language and compiler design?
I think definitely, that's something I alluded to earlier. I think in terms of bioinformatics, identifying the core primitives and operations in bioinformatics and computational genomics is actually really, really hard. Again, because you could draw these very coarse-grained boxes around things like alignment or indexing or hashing and stuff like that. But when you actually look at the concrete implementation of these things, some subtle details, but those details actually have algorithmic implications. So it's really hard to sort of identify those primitives. But I think we're sort of on the right track in giving people a low-level infrastructure to implement these things themselves, actually. So that was one of the motivations behind going with a lower-level language rather than a higher-level DSL. In terms of actual compiler design, I think I don't know, for me, dealing with these generic types and duck typing of Python in a statically typed context has actually been really, really hard. So, what we're doing in Seek is essentially taking a Python program that's dynamically typed by nature and imposing a static type system on top of that. And that can lead to some actually really, really difficult to resolve corner cases. So that's actually been a really hard, on the programming language and compiler design side, that's actually been a really hard problem. And we're still continuing to sort of close the language gap with Python. So there's still some cases that we're working on there. So that's sort of, I would say, on both sides, on the bioinformatics side and the programming language side, those are sort of the two biggest challenges for me, at least.
Do you think that there are other problem domains that would benefit from having a similar runtime available to them? And do you think that there is just an overall benefit to having custom languages for some of these different research areas or different use cases versus having general purpose languages that are broadly applicable but not necessarily optimized, and sort of what you see as the trade-offs and the overall spectrum of programming language availability for solving some of these interesting and challenging problems?
So I think it varies a lot by domain. Bioinformatics is sort of it's a unique domain in that a lot of practitioners are not software engineers or programmers or computer scientists by trade. So I think for bioinformatics, something like Seek, going the Python route and implementing something that behaves and has the semantics of Python was really useful. In terms of general purpose languages versus domain specific languages, I think both definitely have their use cases. I think with DSLs, it's important to sort of have interoperability with existing libraries and systems to be a priority. And again, this is something I mentioned earlier, but I think we don't want to sort of fall into the trap of not being interoperable with other systems, and then someone who uses Seek is sort of unable to use, let's say, NumPy or TensorFlow or some of these other libraries that exist for Python. So I think DSLs are really good, especially if performance is critical. But at the same time, I think interoperability needs to definitely be a priority. And that's something that we've definitely had in the back of our minds as we've worked on Seek. So
what do you have planned for the future of Seek in the near to medium term? And what are some of the overall impacts that you hope to have as it progresses?
So I think in the short term, definitely, we're still working to close the language gap with Python. So right now we have a unidirectional type checker. So most cases we can, do type deduction on. If you have a equals 2 plus 2, for example, we can tell that a is an int. That's a super easy case. But Python actually has some more complicated cases, like, for instance, if you use lambdas in Python, their lambdas aren't typed. So if you sort something, you have like list.sort and some lambda, you actually need bidirectional type checking to resolve the type of that lambda. So we're in the process of actually implementing that right now, along with some other things like optional types, which will allow us to deal with nones. For example, in Python, you can assign anything to none. In the statically typed context is a little bit more tricky. So that's another thing that we're working on. So just sort of closing the language gap a little bit more. Beyond that, we're working on a new intermediate representation that's a little bit higher level than LLVM-IR. And our hope is that will actually allow us to do a lot more Python-specific and domain-specific optimizations. So, in Python, let's say if you have a case where you're adding 3 or concatenating 3 strings, that's something that we could potentially recognize in this new intermediate representation and optimize. And on the bioinformatics side, there are many, again, that case that I mentioned where you reverse complement something twice, that's something that we can potentially catch if we have an IR as well. So that's another project we're really excited about. Another thing I alluded to earlier was different backends like GPU and FPGA, and seeing how those things interact with these various domain specific optimizations. And that's another thing we're excited about exploring. And like I mentioned, working with Google Cloud Life Sciences to run Seek on the cloud and seeing what we can do there. I think that opens up the door to a whole bunch of other domain-specific optimizations that a compiler like Seek could do. So those are sort of the projects that are ongoing right now that we're really excited about. And just getting more people involved in Seek. I think so far we've had a really limited number of people working on it. It's myself and the co-first author on our paper, Ibrahim Numanagic, he was a former postdoc at MIT, and now he's a professor at University of Victoria. So it's mainly been the two of us with a few undergrads, UROps working with us. So just getting more people involved, I think that's really something we're very excited about as well.
For the future success and sustainability of the project, what are some of the risks that you think could pose a threat in terms of its future viability, and what is your thoughts in terms of the level of involvement that you're going to have once you have finished your PhD program?
So for the first part of your question, I think I'll just have to come back to interoperability, because I think that's such an important point. We really want to make sure that if someone uses Seek, they're still able to use these other Python tools and libraries and frameworks that exist today. I think that's something that we're not quite at the place we want to be right now. We have Python interoperability in Seek. So if you have some Python function that's pure Python, you can call it right now in Seek, and we do all of the marshalling to and from Python types between Seek types. But I think, what we talked about, to have tooling and debugging support, that's something that we're actively working on. So in terms of viability, I think that's a really important aspect. In terms of my own involvement, I think this is a project that has, we have a huge laundry list of ideas and things we want to explore. So I'm not yet 100% sure about what my future plans are going to be, but I definitely envision working on this even after I complete my PhD. So I think this is definitely a long-term project, and I'm really excited about it. So yeah.
Are there any other elements of the Seek project itself, or bioinformatics, or language design that we didn't discuss that you'd like to cover before we close out the show?
I think we did a pretty good job, to be honest, covering all our bases.
Well, for anybody who wants to follow along with the work that you're doing, or get in touch, or contribute to the project, I'll have you add your preferred contact information to the show notes. And with that, I'll move us into the picks. And this week I'm going to choose board games as a way to have something to do, particularly in these interesting times. So definitely recommend taking a look at your board game closet or maybe contributing to it. One that I've been enjoying playing with my kids is a game called Labyrinth. And I'll also mention Board Game Geek as a great site for being able to discover and read reviews on different board games as you're determining what new ones to add to your collection. And so with that, I'll pass it to you, Ariya. Do you have any picks this week?
So I would have to go with this documentary that I recently watched called Breakthrough, which is it's not a new movie. I think it was released in 2019, but it's just one that I happened to recently watch. It's about Jim Allison, who's a scientist whose work led to new cancer treatments, and he ultimately won the Nobel Prize because of it. It is a really unorthodox scientist, I would say, and the movie sort of shows his perseverance throughout his research career. And it was a really interesting movie. I'd recommend it.
Well, thank you very much for taking the time today to join me and discuss the work that you've been doing with Seek. It's definitely a very interesting project and one that I'm excited to see some of the impacts that it will have as it continues to grow and gain some adoption. So I appreciate all the work that you're doing there, and I hope you enjoy the rest of your day.
Thank you so much for having me.
Thank you for listening. Don't forget to check out our other show, the Data Engineering Podcast, at dataengineeringpodcast.com for the latest on modern data management. And visit the site at pythonpodcast.com to subscribe to the show, sign up for the mailing list, and read the show notes. And if you've learned something or tried out a project from the show, then tell us about it. Email hosts@podcastinit.com with your story. To help other people find the show, please leave a review on iTunes and tell your friends and coworkers.